structure in designing and the interaction of different institutions. So my work builds on different ideas about institutional structure. So there are different arguments in political science about how, whether, and the degree to which institutions matter. So some might say that institutions create different structures, and how we represent those structures would be by these popular games in game theory. So for example, the way that the structure of the role of the elites, for example, might actually be between the elites in the government or the elites in the military, might be something similar to the battle of the sexes, where there are two groups who have completely different interests that are trying to coordinate in some way. It could be a prisoner's dilemma where they would be better off to cooperate, but there's some incentive for you to deviate, to grab power for yourself. And these could be other possible ways that you could think about how institutional structure might influence behavior. So I'm thinking about the ways in which institutions could incentivize behavior of governmental agents. So this is a pretty broad way to think about institutions, because I could be talking about government-level behavior, or I could be thinking of a smaller, kind of more macro or in-country behavior. So I could be thinking about different laws and how a certain law incentivizes certain types of behavior. So the more macro would be, Barbara Geddes has a work and she talks about the relationship of the elites to the governing body. So how is the relationship between the elites and the government writ large characterized? And she uses different games to represent that. I could also talk about policy. So for example, how do laws about voting influence people? So do they decide to vote or not? So if voting is compulsory, then your payoffs for deciding vote, not vote are a little bit different than if it's optional. Does that make sense?
Are you concentrating mainly on two-person, or yeah, so, well, in game
all
theory,
interactions
two-person.
are, going to be dyadic.
Okay, so coalitions, except insofar as they're hidden under one of the two aggregates. Okay.
Right. So coalitions might be represented. The existence of a coalition, you could argue, might influence the payoffs that agents receive. So if there is a type of coalition, you might say, well, really, there's only these types of behaviors that are available, or they might, because the coalition exists, you might want to choose this action instead of the second action. But right now, I'm starting very simple, so it's just 2x2 games. And as Rick knows, poor Rick, so this is part of an independent study that I'm working on, so Rick has seen this every other week all semester, and I worked on this last year. So at any point, if I fall down, Rick can just come up and get the rest of the talk, probably. But I need to commit to one of these two. And the problem for me has been that I think I could go in both ways, and both are potentially interesting. So I could say, how does the design of a particular law influence compliance with that law? Or I could look at a more large scale, which is probably what I'll do, but that's more complicated because it's just a simple game, you have to abstract quite a bit from that. So political scientists believe that institutions influence behavior. Some say that it is only institutions that matter. So Acemoglu and Robinson have a new book coming out called, I think it's like Why States Fail, Why Nations Fail, something like that. And they say it's all about institutional structure. So it's not necessarily culture at all, or what we think of as culture, but it's just the structure of the institution and the way they incentivize different behaviors. I don't think that that's necessarily true. I think that there is context that really matters, because the way that Acemoglu and Robinson in particular talk about institutions, there's no reason why a change in an institution today would not guarantee or cause an immediate change in behavior tomorrow. But this isn't necessarily what we observe. For example, in the case of Italy, there is the same political institution in the north and the south, yet some would say that, well, many would say that the effectiveness of that institution in the north is dramatically different from the effectiveness of the institution in the south. So it can't be that only institutions matter. There has to be something else. And so I'm using an agent-based model to see if pre-existing institutional structures have an influence on both the path to equilibrium and the later equilibrium that emerges. So the way I'm looking at this in my model is I'm saying that they begin with some institutional structure A, they change the institution in some way, and right now it's very vague, and I'll narrow that down as I go along, but the institution changes in some way, so we have a game that changes to a second game in the next period. And I think it's the order, there's some type of relationship between those games that influences both the time to equilibrium, so how long does it take when you switch games for you to have the stability that we're necessarily looking for, and are we able to reach that? So do all pairs of institutions end up with the same equilibrium? So the model right now is, again, very simple. So those of you who saw me present this spring, this is much less complicated than the previous version. So the model is a round-robin tournament. Round-robin, I play, so if we're all the community, there's two halves, so it could be the elites and the government, let's say. There's two populations, and that allows for possibly different preferences, so that we have two populations who are playing each other. And every member from Team Elites plays every member from Team Government in every round. And the way it's set up right now is there's 10 rounds per play. So I'll play, Adam 10 times if we're on different teams, and then I'll play John 10 times, and then I'll play Doug, and so on and so forth. This is for ease of modeling. And as I decide on a specific framework or a specific example, I'll have to look more closely at whether or not I think round robin is a wise choice.
Question.
Yes.
Why, well, I'll just put it straight out. Why do you assume there has to be an equilibrium?
So by equilibrium, what I mean is the expected behavior of the game. So in Battle of the Sexes, what we expect, and I'll show the payoffs in a minute, is that so the way Battle of the Sexes is characterized is John wants to go to the opera, and I want to go to a boxing match. We'd rather go together than separately, but we each have our preferences. In Battle of the Sexes, what we would expect is that half of the time we would do what John wants to do together. Half of the time we would do what I want to do together. So my question is, do we see that behavior? And so I'll talk a little bit about measures of stability of any certain outcome, but that's what I'm seeing is, do we actually get there? Does that make sense? The model is evolutionary in the sense that after every round, everyone on each team is paired up. So we have in-team selection. Yes?
I'm sorry to interrupt. On round robin, is it always played in the same order, or is the order randomized?
The order is randomized, and so I had a little adventure this summer, and I learned that if you always select, the row players to move first, then, so if John always gets to go first, over time, if we play enough games, we always do what John wants to do, or 70-30 will do what John wants to do. So it's randomized which team moves first, because there could be payoffs. If I go and I play in this order, then there's a feedback. There's a feedback for if I happen to choose what I want to do first, it's reinforced right away, so there's a slight bias. So it's random who goes first every round, and after every round, the list, so I'm just doing arrays, and the array is shuffled.
So just really quickly, does the order end up mattering, I guess, so you say that it's evolutionary with respect to what unit of time?
So if we had 8 players, I just said 8. So suppose that there are 8 players, 4 per team. So something that this model does is you can't switch teams, which in political science we know some people do, but we're ignoring that for now. So what happens is for the evolutionary selection, we look at each team, and after everyone has played, everyone else, everyone on the team is matched randomly to another person. So it has nothing to do with payoffs. It's completely random. So this could be my highest payoff, and they could be matched to the lowest person or to the second highest. And notice that having this randomization means that there could be a world in which I accidentally select a lot of really low people versus a lot of high people get kicked out. And so there are many possibilities there. So that's what happens. And then out of each pair, their payoffs are compared, and the winner is cloned to the next round. And then there's some probability of mutation, which right now I believe is like 30% or something. So with a 30% chance there will be a mutation, which so it's just it could be a state, So they're automata, so it's essentially a Moore machine. So you have different states, and right now there's 4, and there's transition rules. So if you mutate, there's a 50-50 chance that you'll mutate a state. So you'll think that the last time the person cooperated when really they defected. Or there's a 50% chance that your transition rule will change. So before you may have said, if they defect, cooperate. Now your rule might say, if they defect, defect. So that could be a mutation there. And I don't have a compelling reason to argue for why one would be done over the other, so it's just 50%. But if you have any suggestions, they're more than welcome. So the way that it's worked out right now is you play 2 games. So that's the changing institutional structure that I talked about. So this is your first institution. So if we're talking big scale, you could have an authoritarian regime. And let's say that we're trying this new democratic arrangement. Or it could be that there is a law mandating compulsory voting, and then that law is repealed. Right? So there's some change. And so what happens is you play the first game, and the first game alone, for X number of periods. And then there's some change. There's a policy change, there's an institutional shift, something of that sort. And then you play the second game for a number of periods. And right now, I don't have any strong intuitions for how the 2 lengths of time should matter, so they're just equal. But you could have, perhaps this law has been around for a very long time, but this one is for a short time. And right now, I'm just saying, let's just have them be equal and see kind of what we get. And then there's the mutation rate that I already talked about. So here's the payoffs for the game. So this is Battle of the Sexes, which you can see. So here's row, here's column. So we both get payoffs if we coordinate. So we both have the incentive to coordinate. But there's a difference between if we do what I want, so I'll get 3 here versus 1 there, versus what John wants. So if we pick what he wants, or if he does what I want, he only gets 1 while I get 3. If we do what John wants, I only get 1 while he gets 3. And then this is the prisoner's dilemma. Except that I didn't finish changing it. So this would be 4-0 right there. Sorry.
Oh.
Typo. Okay.
Nice try, James.
That's right.
We're on you.
I know. This is something that's interesting. So this is a game that makes you always coordinate, right? You're stupid if you do anything else. This is a game where you always defect. And then I have a game where it's smarter, or always cooperate. This is a game where it's smarter to cooperate. Here there's an incentive to match, to coordinate, but it's just wiser to do one over the other. And I'll talk more about why I have that in there in just a little bit. Are there any questions?
So do you just have a particular suite of games that you're interested in, or are you considering like all possible games that could be all possible 2x2 games?
So the way that I picked these games to begin with is from Getty's paper, where she talks about the different authoritarian relationships. So what her paper actually talks about is not quite this. It's about what it takes to overthrow the government. So her paper argues about, she says, well, we shouldn't expect all attempts to change institutions to be equally successful, because the type of game that the agents are playing is going to influence the way they try to overthrow the government. And the way they overthrow the government might actually say something about success. So this is where the games came from. But I think that there will be some changing, because she doesn't have any strong reasons for why she came up with them, other than that they seemed like good ideas. So I'll work on that as well. If in doubt, you should just assume I'll work on that. Any more questions before we go to the actual results? Okay, so I started out, I'm still working on better ways to represent the data, but this is what I have so far. So what this is they're playing only one game. There's no switching. And I have them playing it for 500 periods. And so this is Coordinate on C, which is the game where it's 3-3 and 1-1 and nothing on the diagonal. And you can see that this is a pretty easy game, meaning that they're able to figure out there's only one path to payoff. And they follow that path pretty quickly. And even though this graph is pretty large, you can't really see that there's bounds around the dominant strategy, and the bounds are confidence intervals, where 95% of the runs, which is 100 runs, I believe, 95% of the runs would have this as the outcome behavior. Now, compare those bounds, for example, to Prisoner's Dilemma or Battle of the Sexes. So in Battle of the Sexes, these two graphical displays are not as useful because in Battle of the Sexes, you essentially have two outcomes happening with equal, so it's bimodal. You're either at CC or you're at DD. So, yeah.
It looks to me that those bounds go above 1 and below 0.
Right, so it is absolutely uninformative. You can't statistically distinguish the other from, you can't distinguish one from the other. So, for example, here you can say that they're picking CC, right, because this is more of a certainty, versus here, you can't say that DD is the dominant outcome because you're, in any given run, it ends up between 0 and 1. I mean,
So I understand that it ends up between 0 and 1.
So why are the bounds
How
so
does it end
large?
up between -0.2 and 1.3, whatever there's on
Because the way that I calculated the bound was just the standard error over the runs times 1.96. So if I wanted to be like to demonstrate the mathematical possibilities, I would pin this to 0 and 1 because you never have less than 0%. You never have more than 100%. But for me, I thought it was informative because it shows that you don't really know what the dominant outcome is. So eventually what I'm going to do is plot the all of the different runs so that you can see how the runs end up, because that will be more informative for this type of game. But I don't know R very well, so Adam is going to help me with that.
Could you explain a little bit the colors?
Oh yeah, sorry. So green is CC. So what I'm just looking at right now is which of these four outcomes do we see. So later versions of this model in my work will look at strategies that develop. But right now, what I'm saying is, at the end of all of the rounds, how many of the players ended up at CC, at CD, at DC, and DD? And so there's only 4 possible outcomes, which are represented by 4 colors here. So CC is they both cooperated. And then in this graph, everything else is down here, and that's the CD, DC, and DD. Versus in Battle of the Sexes, you can see that there's CC and DD happening with near identical frequency. The near identical is that problem with the which player goes first slightly biases, so I need to have more runs of this model so that they should be both 50%. Although I guess I could have a bias in that one agent always gets to move first. But in terms of the expected equilibrium, I would want to have it completely randomized. And because there's a slight bias for DD, you'll see that DC is a little bit higher than CD, which ideally it should look like, if I were to use this graph, like this, where it separates, where you have CC and DD here, and DC and CD here at 0. Does that make sense? So all of this is to say that it's generally well represented graphically, except for those two. But in the single run, agents are doing what we expect them to do, which we can talk about how smart people are compared to agents. But right now, my model is consistent with what we would expect. And this is important because I then switch games. So what I did was there are 3 games here. So it's Battle of the Sexes, which is the 50-50, and then it's followed by Coordinate C, and I'll write the games on the board so that you don't have to memorize them, although there's no eraser. So sorry.
Yeah, right here. You can erase all that stuff from the meeting yesterday.
Thank you. Okay, so that's coordinate on C. And then there's what I so cleverly call all C. Oh. And then all D. And then we saw the expected behavior. Everyone should be cooperating here. Everyone should be defecting here. And everyone should be cooperating here. we wouldn't necessarily expect an equilibrium that these two would be different. But we could see how having this payoff here might influence how people learn, which we'll see. So battle of the sexes, generally they're equal. Again, I should do more runs so that these two lines are overlapping perfectly. So for the first 500 time steps, everyone is playing Battle of the Sexes. And then for the second 500 time steps, they switch to a second game that is either this, this, or this. So these are 3 separate runs that I've done. And so you can see that even though the institution changed at time 500, we don't really notice this sort of separating to be distinct until perhaps between 600 and 800. So there's a little bit of a lag in the learning curve, which makes sense to us, right? So you would think that people aren't going to automatically adopt the best strategy T+1 after the change. So the question that I'm looking at is, how long does it take for people to learn the new optimal strategy, and is that period of time important?
Just to understand on this,
Mm-hmm.
the institution switches for everybody at once.
For everyone
So it's
at
not
once.
as if some of us suddenly find ourselves in a new circumstance. So
Correct.
it's the relationship between elites and the government has fundamentally changed for everyone at the same moment.
Right. The IMF came in and said you need to do these changes to get a loan, and so these changes happened, or a law is repealed or created or enacted. But having kind of rolling changes would definitely produce a different outcome, I think. So,
Jim,
yeah.
if I may interrupt. So, and that relates to the thing that I do talk about last day. I'm just curious the way you define institutions and whether this is relevant. Sometimes institutions are enough flexible that a change in some of the rules do not actually change the institution. So I'm not sure how that's reflecting your
There's 2 questions there that are really interesting. So one thing would be, so Dimitri's talking about the types of change. So maybe the games that I'm using are not necessarily representative of all types of changes we might expect. And that's what I'm trying to get at with having both all C and chord on C here, because if you switch, for example, from all D here, you would expect agents to learn faster because there's only one payoff. Versus if you switch from all D to coordinate on C, you might expect that old behavior to linger because there's still some reinforcing of that choice. It's not as wise necessarily, but you still are getting rewarded for that choice. So that could influence things. Is that what you're saying? There's also a change. So something that's interesting that I didn't have here, well, I'll tell you that point and I'm going to write it down. But I'll come to that in just a second. So what I see here is a difference in how long it takes to reach what we would call equilibrium. So there's a couple of points here that are a little bit sticky because, as John brought up before, am I assuming that they reach equilibrium? Another thing you could say is, how do you define equilibrium? There's different ways. So I could say the proportion of change in that behavior. So in the last 100 runs, has it been 95% of the time I'm seeing this outcome? So there's different ways that I could categorize equilibrium that I'm just starting to think about now. But in the preliminary part, what I'm seeing is we do end up at the anticipated outcomes. So when you are playing coordinate on C, you expect the outcome to be CC, and that is what we're seeing. When you play all C, we expect it to be all C, and that's what we're seeing. And when we go to all D, we expect it to be DD, and that's what we're seeing. The thing that I think is interesting is the period of time it takes before these bands separate, before the outcomes are distinguishable, before we can say that we are certain that CC is what's happening over all of these runs. And again, how I define this equilibrium will be dependent in some sense on a time. So how I define it, I might be able to make that claim, at 950 versus 975. So different definitions may influence the outcomes that I am determining, but the general behavior is what we would expect. But the slope of the lines is a little bit different. So for example, all C and all D are pretty much graphically identical. If we colored that purple, these two would look exactly the same. Does that make sense? Versus if we overlay coordinate C, this result, over that, this slope is steeper, and our bounds go in much faster. So what this says to me is that people are learning much faster, so this institutional change is incentivizing the new behavior. So the institution is essentially more effective in this case than here. So if there is an institutional change to bring about CC, so you're saying, we want to change the structure of institutions so that people end up at CC. People are going to end up at CC much faster in this model, well, perhaps much faster, but faster in this model than in this. And that's because there's no incentive for you to linger on that D outcome, which is what Dimitri was talking about. Because in Coordinate on C, if you were in Battle of the Sexes, so that is there was some payoff for you before to be here, and there's still some payoff to be here in Coordinate on C. So behavior, the ultimate behavior of the agents converges slower here than here. So the question I'm interested in looking at is, does that matter? Is this time significant so that different institutions matter, not only in the types of outcomes that they're going to bring about, but the way in which they bring those outcomes about? Deb?
So, bringing it back to like your example from Italy, right? It doesn't seem to be the case that the institutions in the north just move more slowly than those in the south, right? So that the slope of convergence to equilibrium is just slower, but like it doesn't seem to be converging to equilibrium the way it does in the south. Your model seems to predict a convergence over time, and it's just that the institutions in the north will converge. It's just over a greater number of periods. But there seems to, but like in actuality, what we observe is more discontinuous, where institutions like don't work, and then all of a sudden some exogenous shock occurs, and then they do work. If that's what you're trying to capture in this model.
So Italy could be different. It could be that the institution, so rather than having chord C be 3-3 and 1-1, it could be 2-2. Where there are these patterns in southern Italy, so there's something about the strategies that are still incentivized under this change, and so we don't observe the change because it is so slowly. So there is something on institutions in southern Italy not being effective, despite being the same in the north and the south. And it could be that they're not converging slowly. It could be that they're effective in some ways and not in others. So it really just depends. You know, is it uniformly not effective across the south or in certain ways?
To build on that, one thing I noticed here is that all of the games that you are switching to are single equilibrium games.
So something
one way you might think about Italy is, at some point in the past, they were playing a game, and then it switched to a game that has two equilibria. In the north, they converged on a cooperative one. In the south, they converged on an effective one, or whatever you want to call it. And there was something about that fork in history that accounted for that. The way you So it would be really easy to build this into your model.
So I have it.
Oh, okay. I will wait for that slide then.
It's not a slide, but I'm going to talk about it. John?
It seems to me, but I could be wrong, that this is going to depend heavily on the mutation rate. I mean, if there's no mutation, then whatever the initial configuration is going to remain. And if it's high mutation, there's no memory. And so it seems these curves would be, and that might be either institutional, that the south is more flexible than the north, for instance, higher mutation. But I can think of a lot of correlates with mutation rate, but it seems your curves are going to depend an awful lot on that.
So that's true. They are dependent on the mutation rate. And at one point, I couldn't understand why, when I switched the games, they weren't learning, and it was because there was no mutation rate. So that is completely true. If there is no mutation rate, there is no learning, and once they do something, the end, that's what happens. So my goal for this weekend is, I'm meeting with Rick next week, and I told him I would start working on looking at how sensitive it is to the mutation rate.
Yeah.
I think it can go plus or minus 20% either way. So I'm at 30 right now, and I think I can go, time extends. It takes them longer to learn the lower the mutation rate is. And if it goes too high, then it's just uninformative, and then you have chaos, essentially, because there's no way to really select.
Okay.
But there does seem to be a decent band, for my clicking in different mutation rates that support enough learning that they are able to find the equilibrium but not so much that it's uninformative and not too little that they don't change at all. But no, that's very true.
Yeah, it's, this is a broader question that you're not tackling, but, until relatively recently, till the 20th century, essentially, Italy was a bunch of city-states.
Mm-hmm.
And that clearly influenced an awful lot of went on.
So that's
ever
why I
after.
really want to look at the strategies, because I think you could talk about the differences in the city-states as incentivizing different strategies and how those strategies influence behavioral outcomes. I'm not there yet technologically, but that is a goal because I think that's going to be, so I think that this is definitely interesting, but I think the strategies are going to be the really fascinating part that I might be able to do something with. Pamela, did you?
Yeah. What happens if you run the model for more time? Are you going to see that is it stable?
Generally, I run it up to 1500, and what happens is, especially in in both the one equilibrium and the two equilibrium, so coordinate C or whatever, and then battle of the sexes, the bands tend to get smaller. On battle of the sexes, the bands don't necessarily get smaller, but you see the same thing, so there's not distinctive changes. The way that you would expect to see the changes if I did ramp up the mutation rate, then perhaps over time there would be more fluctuation.
It reminds me the evolutionary stable strategies, and so I think you can write down the equations, and then you have an equilibrium, and then you can do in the civil, invasive analysis at those conditions and calculate the new equilibrium. It's not going to tell you anything about the time, but
That's also my goal for next semester. Anything else on this? So the thing on Abe's point that's interesting, and I wasn't sure how long this would take, so I didn't make the slide, so I'm very sorry. But I have the opposite of this, so you're at coordinate on C, for example, and you switch to battle of the sexes. And the first time I did it, what happened was, so coordinate on C, you have CC up here and everything else down here, right? And then when you switch to battle of the sexes, what was happening was it just continued. But then I increased my mutation rate, and so now you do see a little bit of this happening where you move toward the expected equilibrium. So this would be all C, and then this would be battle of the sexes, which is another really interesting institutional design question. So what this is essentially saying is that even though there are two outcomes that you could be selecting here, because you've been playing this one for so long and because this one still does well under this paradigm, you don't see a shift. So this could be examples of failed institutional changes, right? So you think that you're making this great change in the institutional structure, but you observe the same behavior. One possible explanation would be that the old behavior is still permissible or being rewarded under this new institutional structure.
On
Yes.
Battle of the Sexes,
Mm-hmm.
my understanding is that Battle of the Sexes is sort of like a coordination game in the sense that there are two equilibria, which is one, everybody goes to the opera, two, everybody goes to the baseball game. There's no mixed strategy equilibrium there.
Right. So what I mean is that half of the time, so what happens is half of the time in normal Battle of the Sexes, the reason why it's like this is because half of the games end up at CC and half of the games end up at DD, which is why this graphical representation is not informative. What you'd really be seeing is CC, and then just as often you'd be seeing DD as the outcomes. So half of the games would look like this.
Half of the games, you mean half of the time,
Half of
all
the runs,
of the elites,
correct.
and, okay, but within a given run, everybody's going to coordinate on a single outcome.
Yeah, sorry, I wasn't being clear there.
Okay.
So what I'm saying is that in any given run, everyone ends up at either CC or at DD. There's no mixed strategy. So mixed strategy is something about beliefs and uncertainty that I don't get into. So we would expect these two outcomes are equally likely, and we see one of the two, which is why they occur with 50% frequency, because there's only two outcomes. Here what we see is if the mutation rate is low enough, no one experiments in a sense. Because to move from a CC to the DD, it has to be a joint coordination. If either of you makes a mistake, you don't get any payoffs for it, so there's no incentive. So there's a few failed mistakes, but you would both have to make a mistake in order for you to get a payoff. So if the mutation rate is low enough, or there's not enough people jointly making those mistakes, you see, even in Battle of the Sexes, you only see CC as the outcome. The higher the mutation rate, the more likely you see the 50-50 outcomes, or 70% of the time everyone is still at CC, but 30% of the time they shift to DD.
So just a quick thought on analytics there.
Mm-hmm.
If you use large pools of agents, you can probably prove what the threshold is there.
Okay.
You could probably come up with an analytic solution for how much mutation you need to escape the basic, the basic action.
Yeah.
Actually, I think the answer is if it's a large pool, then you need very, very high mutation rates because everybody needs to coordinate at once. Because a small minority that tries switching is always going to get voted down over time.
Yeah. I think I agree with that. Yes. So the next thing is going to an analytic solution and showing how this compares to that. So there's a few next steps, which I think I have. Oh, yeah. So I'm going to do the experiments as soon as I remember how to do them. And I'm going to vary the period, so how long the time is, and the different measures, such as mutation rate, the payoffs. Ideally, I would like to mess with the payoffs to see if there's a relationship between how big the payoff is and how quickly you change. And later, there's not one more. I want to do the analytical side of it. So this is one small piece in a very big puzzle, and I'm slowly kind of marching toward putting pieces together. Should I do that?
So in that respect, are your payoffs ordinal, or do they actually, or is it typical game theory, or is it
like where do the numbers?
Like 2 times.
So that's what I'm going to try to do, is to have some type of relationship where if the payoffs are equal, maybe I might see this, and as the payoffs in this game are double that, then they learn that. I would like to have something more general like that. But right now, it's what numbers do I think sound good.
One thing, and I know you've got plenty of reading, but to underline, it might be worth your while, first of all, to put this in the context of evolutionary strategies. I think that's a good idea. And the other thing, without trying to match it or anything, but put it in the context also of Brian Arthur's L-Ferrol problem.
About things like that too. If anyone has readings for analyzing this or different ways the agent-based models have been used and analyzed in a more rigorous fashion, I would be much obliged if you would send those links to me or tell me about them so that I can read them, because I feel like I'm just kind of making this up as I go along.
Have you ever thought about putting this in a spatially explicit context, or has anyone else done that?
With respect to how the agents are constrained with their interactions, or
like who they interact with.
Yes. So I thought about that because so if I'm talking about perhaps like legislators, it might make sense that legislators interact and everyone else in the sense that we all vote together, but it doesn't necessarily make sense that I'm going to interact with every single other legislator. So yes, I've thought about that, but it sounded hard, so I didn't do it yet.
I have a question. So right now you're studying. I'm seeing the switching game is pretty interesting. So right now you're studying from the from C game to the battle of the sex game. So I just wondering, if you switch, it's starting from the battle of the sex and then go to the C game. So what is the result? So
here they go, the different C's, they both go pretty similarly. The all C is a little bit steeper, but from Battle of the Sexes, in all C, because there's no incentive, so let's say that we're in the world where we ended up at DD, playing Battle of the Sexes, and then we switch. Because there's no incentive for DD any longer, we're going to quickly move to all C. Versus in coordinate on C, if we're at the DD outcome and coordinate on C, this is 1-1, there's still some incentive for DD, and so we might learn a little bit more slowly. because we can still pick this. And the reason why we're learning more slowly, in a sense, is because we're selecting people based on their payoffs. And so you're still getting some payoff here, so the selection isn't biting as much as it would. The difference between the two isn't as dramatic here as it is here. I would imagine that if this were 4-4 and 1-1, so the difference between 3-3, I think that the learning might be more similar. But I think it's because these two payoffs, the difference between them is more similar, that they're learning more slowly.
So maybe you can do something, average fitness of the population might be different, because some individuals have a...
That's a good idea, and that would probably be really good for guiding intuition about the differences in the games when I'm thinking of payouts.
Jean, have you played with information structure? On the perfect information, some actors?
No, so that was the previous version of the model. Okay. There was a difference in kind of how, it's too complicated for right now, but later I would love to look at things like that.
So you keep saying mutation rate, and I think it's really funny to think about like the elites mutating. It makes me, we have like a zombie government or something.
Sometimes that's not wrong.
Right. Fair enough. But until we're talking about that kind of government, it makes me wonder what exactly the real world analogy is to that, and how you would ever measure it, right? So it seems like some kind of adaptation or learning or something. So it's people who are willing to experiment on the sorts of policies that they try, or their approaches to negotiation, right?
Even though it's called mutation rate, it could be something like experimentation, where you think, we've always done it like this, but now I think I'm going to do that. Or it could be a mistake where you forget or you get confused or whatever reason. So even though it's called mutation rate, it's not necessarily as though they're mutating. I mean, that's the simplest way to talk about it, especially in the context of these types of models. But I think it could just as easily be a random experiment. It wouldn't be an intentional experiment, right? Because it's completely random which transition they switch, and we would think intentionally that they would be waiting on which transition rule they're changing. They might think, oh, this is the one I want to change.
I guess what I'm saying is stability and change in the model depend on that assumption that this is how policymakers decide to switch. And what you've got is clean analytically, but I just have a hard time telling a psychological story that really, Boris Yeltsin did this, he switched states because of that. I feel like you're going to have a hard time when you take it back to Haven, selling Siebel in this part of the model.
So the previous explanation for it was like diffusion, learning, diffusion, intentionality. That's
but
difficult.
That doesn't work here because people are coming up with it totally independently.
Right, so that would be the next way. So this is a random diffusion, we could say. Yes.
Let's say, also, you can think about it differently. Think about it in terms of leadership turnover, right? Like who are these elites, and do the same. Is it the same? Are you conceptually thinking of the elites being the same, the exact same set? Like you've got a change going on here, and that's something that varies.
So
these are Tea Partiers who are being elected because they want to try something different. See how it goes. They'll die off if it doesn't work.
Once I'm able to analyze the strategies, I would like to play around with that because I think it would matter. But right now, since the strategies aren't being analyzed and don't play, they play an important role, but they're kind of behind the scenes right now. It doesn't make sense to mess with this, but later I will. So something I think could be really interesting because I'm interested in culture, and then I'll wrap up, is so they had a huge freshman class in Congress a while ago, so they had like orientation sessions, which in terms of the model, you can think of them as going for everyone saying, well, this is the strategy you want, but now we're telling you this. So you could think about it as intentional change. So when you're reorienting people, it could be like a massive switch or changing this to 0, something like that. And there could be people who get confused or have their own bias who don't do that. So that could be another way you would think about mutation rate in terms of real political examples.
I was going to say also it could be their individual background. The elites don't come from, drop out of the store. They come from a particular process, and that means, and that involves the circulation of ideas and the mutation of ideas, right? They go through particular educational establishments. They go through particular, and you could think of that as being sort of where are we getting this variation? Actually, over time.
If I were letting you into the master plan, this is the part where I tell you I think that this is where the culture part is really going to come in, because you have this community. I would really like to analyze am I seeing this strategy even with the mutation rate? Do I get to see the same or very similar strategies in my population? So how homogeneous or heterogeneous is my population? And I think that so again, all of this is interesting, but I think that is really the part where I'm going to be able to make some great conclusions.
Gina, along those lines, if you think of positions in state space, to sort of use the notion of position, and then you have queues, so people switch queues in state space, and mutation would be like diffusion, but you could have you could still do the analytics on that.
So what you mean is this is my population and I have clusters.
Yeah. That
so,
seems to be much more cultural somehow.
And then I'll move, for example.
Yep.
I think that could be
you
good
could
too.
still, that's still open to analysis, that kind of thing.
That's how I had started this, and I cleaned the code up some, but there's still kind of like some vestiges of being able to see people's places as they run around. But when I was making this, I just had such a hard time deciding, because all of these things are so fascinating, but I went overboard on the intricate details last time, and it was just intractable. But I might ask you more questions about this sometime, because I'm really interested in it. Right? Yes?
You might want to revisit your selection algorithm. It sounded like from what you said you were doing a tournament selection. That's going to probably affect what happens when you change the relative weights.
Within each team. Yeah. I'm not really that comfortable with how much this model depends upon the round robin and the selection. And so I want to look at other models to see how they've done it, to see if I can think of a better way to make sense of it.
Well, you'll get these same results, though. If you had people every turn you play a random opponent from the other side, just one random person, you get the same result.
Yeah, I think that this is I actually think that this is speeding the process up, because you're guaranteed to play everyone. I mean, it's homogenizing the population and that everyone interacts with everyone else, so I'm not getting the same type of pockets. And because there's 10 rounds, I think that I'm increasing the rate at which people are able to learn, or the population is able to learn. Okay, thank you guys very much. And my email is jclip, so if you think of anything that I should read, I will read it.
Okay.
Thank you.